What if two losing strategies could be combined into a winning one? Welcome to Parrondo's paradox, the counterintuitive mathematical quirk where losing plus losing equals winning. Imagine you're at a casino, and sitting on the table are two games to play. Both of these games are rigged against you. Over a long enough timeline, if you play either one exclusively, you are guaranteed to lose money. Now, common sense tells us that if both games are losers, randomly switching between them should just give you, well, two slightly different flavors of losing. But mathematics has a surprise for us. If you combine these two losing games in just the right way, suddenly you win. How exactly is this possible? Let's break down the games, starting with Game A. Game A is dead simple. You flip a slightly biased coin. You win $1 with a probability of 49.5%, and you lose $1 with a probability of 50.5%. It's ever so slightly unfair, just 0.5% in the house's favor. If we calculate the expected value of a single flip, we see that on average, you lose exactly 1 cent per round. It's a slow bleed, but over a long time, your money inevitably drifts downward. Game B is a bit trickier. Instead of a single coin, Game B looks at your current bankroll, your capital, and uses that to decide which coin you flip. If your current capital is perfectly divisible by 3, say 0, 3, 6, or $9, you are forced to use the bad coin. And this coin is terrible. You only have a 9.5% chance of winning. But if your capital is not a multiple of 3, you get to flip the good coin, which boasts a very generous 74.5% chance of winning. Sounds promising, right? The trap is that the math forces you to land on those multiples of 3 just often enough that the bad coin drags down your overall average. You are stuck in a modular trap, making Game B, once again, a net loser. Let's watch Game A in action. We'll simulate 500 rounds of this biased coin toss. Notice how the graph behaves. Sure, there are little peaks and valleys due to variance, but the overarching trend is undeniable. The relentless 50.5% chance of losing slowly grinds your capital down below the zero line. Now let's simulate Game B over 500 rounds. Remember, you have that incredible 74.5% winning coin most of the time. You might see some sharp upward spikes, but eventually your capital hits a multiple of 3, the trap triggers, the bad coin forces you to lose, and you get pulled right back down. Just like Game A, you end up in the red. Now for the magic. We know Game A loses. We know Game B loses. Let's play them together, alternating. Play Game A twice, then Game B twice. A, B, B, repeating. Watch what happens to your capital now. Both individual games go down, but the combination goes up. And it's not just a strict alternating pattern. Even if you completely randomly choose between Game A and Game B at each step, shown by the yellow line, the result is the same, an upward trajectory. Two losing games have combined to create a winning strategy. To understand why this works, we need to look at Game B's Markov chain, a map of its states. Your capital, modulo 3, means you are always in one of three states: 0, 1, or 2. When you play Game B alone, the probabilities naturally funnel you into state 0, the trap, where you are forced to use the terrible coin. You spend too much time here, which keeps your expected winnings negative. Game B alone. Steady-state clusters near state 0, the trap. But when you interleave Game A, the simple coin, you inject a new dynamic. Game A doesn't care about multiples of 3. It acts as a scrambler, shuffling you out of state 0 at a completely different rhythm. It disrupts the trap. If probability maps aren't your thing, here's a beautiful physical analogy. Imagine a ball resting on a gently tilted, sawtooth-shaped ramp. Gravity is constantly pulling it down. That represents the downward drift of our losing games. But what happens if you periodically switch the ramp's shape? As the floor shifts, the ball gets caught on the teeth of the new ramp, effectively ratcheting upward against gravity. That periodic switching is exactly what alternating our games does. In physics, this is known as a Brownian ratchet, and Parrondo's paradox is its game-theoretic cousin. To really prove this isn't just a statistical fluke, let's run 100 independent simulations all at once. The red bundle shows 100 people playing only Game A. The purple bundle is Game B alone. Both masses clearly sync. But the green bundle? That's 100 people alternating the games. The trend is unmistakable. It's a robust, mathematically guaranteed phenomenon. The key is the stationary distribution over the Mod 3 states. In Game B alone, state 0, the trap, has high probability, nearly 38%. But when you interleave with Game A, state 0's probability drops dramatically, down to just 22%. Less time in the trap means more winning. Parrondo's paradox isn't just a mathematical curiosity. It shows up across science. In physics, it's the Brownian ratchet. Random thermal noise plus an asymmetric potential drives molecular motors in your cells. In biology, individually harmful mutations can combine into an evolutionary advantage. And in game theory, it challenges our deepest intuitions about strategy. One principle, many domains. So what's the takeaway? 2 losing games, 1 winning combination. The secret is disruption. Switching breaks the trap. Sometimes the whole really is greater than the sum of its parts. Losing plus losing equals winning when you know how to switch. Thanks for watching, and don't forget to subscribe. See you in the next video!